In this video, we are going to discuss about the solution of numericals based on Arrhenius equation. Arrhenius equation normally appears in two forms. We'll call it form 1 and form 2 will be discussed afterwards. And we'll be talking about numericals based on both forms. This is the most popular form of Arrhenius equation where K1, K2 are the rate constants at temperatures T1 and T2. EA is the energy of activation and R is the universal gas constant. This is the second form of Arrhenius equation where A is the pre-exponential factor, EA is energy of activation, R is universal gas constant. Now this is a very important slide. These are the things you need to remember before you start solving the problem. First of all, the temperatures T1, T2 should always be converted into Kelvin. Normally, in a numerical, temperatures are given in degree centigrade. If it is given in Kelvin, then you don't have to convert anything. But however, if the temperature is given in degree centigrade, you have to convert it to Kelvin by adding 273. Normally, energy of activation in a numerical is given in either kilocalories or kilojoules. You have to convert it into calories or joules respectively by multiplying by 1000. And third, the value of R depends on in what unit energy of activation is given. If energy of activation is given in kilocalories, R should be used as 1.987, and if energy of activation is given in kilojoules, the value of R to be used is 8.314. Now let's talk about few examples. This is the most common form of numerical where you are given two K values at two different temperatures and you are asked to calculate the energy of activation. The point to be noted over here is that the temperature is given in degree centigrade. K values are given, they have the same unit. So let's write on the given. K1 is given, K2 is given. Temperature T1 is converted into Kelvin by adding 273. And this is the form of Arrhenius equation. We substitute the value log of K2 by K1, energy of activation. This cancels, so it becomes log of 2. This to multiplication is 4.576. This subtraction comes here, and energy of activation can be calculated as by the solving this numerical. And the answer is 12.810 kilo 87 calories per mole. It is not required of you to convert it into kilocalories. You can leave the answer as such. In the second type of example, instead of giving the value of K, what is written is at two different temperatures, it is written that K value is 5 times or 3 times or 2 times bigger. Over here in this numerical, it is 5 times. So if we assume that K1 is K1, K2 should be 5K1. Rest is the same, temperature is converted into Kelvin by adding 273. And in the solution, instead of K2, we will write 5K1 and K1 appears as such. And rest is the same as in your last example. The solution will give you the answer of energy of activation. In the third type of example, first of all, what must be noted is the reaction is of first order and you are given the half-lives at two different temperatures. Time required for 50% completion is nothing but half-life. Half-life of the reaction at 27 degrees centigrade is 30 minutes and at 47 degrees is 10 minutes. And you have to calculate the energy of activation. Again, let's write on the given. T half 1 is given, T half 2 is given, temperature 1 is converted into Kelvin, temperature 2 is converted into Kelvin. We know that for a first order reaction, half-life is related to the rate constant by this equation. Now, there are two ways of solving it. I can calculate K1 and K2 by calculating T half 1 and T half 2 and substituting as such. But there's an easier solution. Instead of calculating K1 and K2, if I substitute the value of K2 over here, K2 will be equal to 0.693 upon T half 2 and K1 will be equal to 0.693 of T half divided by T half 1. 0.693, 0.693 will get cancelled and this equation simplifies to this. Just keep this in mind that over it is K2 by K1 and in this second equation it is in terms of T half, it is T half 1 by T half 2. You should not change this order. It's 2 by 1 in rate constant. In half life it is 1 by 2. Now rest is very easy. We substitute the value of T half 1, T half 2 and the solution is exactly the same as in our previous example. Now this example is about the using the second form. Over here, energy of activation is given as 105.0 kilojoules per mole. Please keep this in mind. It is in kilojoules now. The rate constant is to be calculated. The frequency factor is given as 2.5 into 10 raised to 15. The temperature is given in degree centigrade. So what are the given? A is given as, now energy of activation is in kilojoules. So now I convert it into joules by multiplying by 1000. Temperature is converted into Kelvin by adding 273. Now solution. Now I just substitute the value K is equal to, this is the value of A, e raised to minus energy of activation. Please remember it has been converted into joule by multiplying by 1000. R value is taken as 8.314 because the energy of activation is given in joules and temperature is in Kelvin. Now I solve this equation. Now this exponent terms becomes minus 42.098. Now, how do we solve this on a scientific calculator? First of all, what I need to type is minus 42.098 has to be typed on the calculator. Then press for the key E, you press Shift and Ln. So you press Shift, Ln and type this number, or if you already had typed it, press Shift, Ln, answer. This will give you this value of 5.23213 into 10 raised to minus 19, and you already have this number. Multiply this, you get the value of K. And the last numerical is, in an Arrhenius equation, A value is given, energy of activation value is given in kilojoules. Please remember this, it is kilo and it is joules. The reaction is first order. You have to find out the temperature at which the half-life is 10 minutes. So let's write down the given. A value is given, energy of activation is kilojoules. I convert into joule by 1 by multiplying by 1000. R value is taken to be 8.314 because energy of activation is joules. T half is given in 10 minutes. First of all, I calculate the rate constant because it's the first order, so rate constant is equal to 0.693 by T half. So 0.693 divided by 10, so this comes out to be 0.0693 per minute because I took T half in minute. Now this is the Arrhenius equation. I substitute this value here. 0.693 is equal to, A value comes here, 4.0 into 10 raised to 13, e raised to minus 98.6 into 1000 because energy of activation has been converted into joules by multiplying by 1000. Then 8.314 because this is in joules, so R has to be taken as 8.314. We don't know the value of T, so T appears as such. Now, solving this equation, this A value will go as the denominator of this value. So this equation simplifies into this 0.693 divided by 4.0 into 10 raised to 13, and this side remains as such. Solving this left hand side, we get the value of 1.733 into 10 raised to minus 15 is equal to this value, and I take the log of both sides.
So it becomes ln 1.733 into 10 raised to minus 15 is equal to minus 11.11859.51 divided by t. Solving the log of this, so t is equal to minus this value divided by log of this. Log of this value will come in negative, that minus and this minus will get cancelled, and t value is calculated to be 348.92 kelvins. I hope this video helps you solve all the numericals based on Arrhenius equation. Thank you very much.